Ladies and gentlemen, welcome to our session, Converge and Conquer, about OpenStack converged compute with software-defined storage. So, I have with me Jacob Caspi from AT&T. I have Christian Reis, Kiko from Canonical, and I'm Christian Huebner from Mirantis. We've all been working very heavily with Ceph over the last few years. And today we want to present to you a way to converge computing and Ceph software-defined storage to get an advantage out of the number of servers that you have. In the traditional model, we have servers, we have storage, and even in the cloud, this model is still present. You have an OpenStack cloud that has compute nodes, that has storage nodes, and while they are now virtualized, you can have workloads, multiple workloads on one server. The one thing that you still have is the separation, and the separation has a couple of disadvantages. So the idea was, as the storage is virtualized too, you don't have an operating system that is proprietary and cannot run on your hardware. You can sort of virtualize the storage too, and that gives us the opportunity to converge the compute and the storage into one. Which you see here, you have, instead of having compute nodes and software-defined storage nodes, you would have hyper-converged nodes. But before we launch into that, I would like to point out a few caveats. As everything, you have advantages and disadvantages. One of the disadvantages, of course, is that you have a higher administrative effort. If something breaks, you have to consider both the compute and the storage part to fix. In very small clouds, you will also have contention between the performance required to drive the disk drives and the performance required to drive your compute. And this leads to the third point that was supposed to be indented, not too many drives per node, especially if you have a small cloud, limit yourself to 4 or 5 drives per node and you will be okay. And finally, make sure that if you have extreme high CPU workloads, that there's enough overhead left to run your Ceph. I would like to hand over now to Jacob, who is going to, to
Kiko.
Kiko, who
Sure.
is going to do the next slide.
Yeah, and since our second slide starts with caution, this slide sort of frames like why and what is hyperconverged in practice. So hyperconverged, when you do look at a hyperconverged cloud, every node is identical. The hardware is the same, and the configuration on those nodes is as much as possible identical. Why do we want every node in the cloud to be the same? I mean, apart from the fact that this is how Google, Amazon, and Facebook build their general purpose clouds. So first, it allows you to build smaller clouds. If you're in the edge and you have 8 nodes, you don't want to allocate 3 nodes to storage, 2 nodes to a non-HA control plane, and then be left with 3 nodes for compute. You want to take advantage of the fact that you have those servers there and that none of those specific components there are enough to max out the servers. In fact, what we see in large and small clouds is that it's perfectly possible to collocate all the services there. But there are also like practical things, such as having a small number of replacement SKUs. If you have specialized nodes for storage and then for compute and then for control plane, and you have 10 different POPs, you need to have replacement units of each of those 30 different server types in each of the POPs. That doesn't scale. So having the same infrastructure, the same configuration, the same hardware everywhere leads to very good operational qualities.
So what's driving AT&T to look at this architecture? We have currently somewhere over 100 deployment of OpenStack in multiple locations. Fairly few small ones, but most of them are located in edge area or edge sites where we are limited to fairly few number of servers per location, somewhere in the dozen to 2,000 servers in location. And the other thing that we are limited there is, of course, space and power, because these are older locations. They used to be central offices, or they are still central offices. So we were looking to achieve 2 things. One is reduce the number of devices and the variation of devices or servers that we put in to our location, and the other one is get a much higher efficient utilization of our existing compute to take, so we don't have to dedicate space and power to dedicated storage arrays, as an example. So one of the ways to get that deployment, as Christian mentioned, is to limit the number of storage devices on the compute to a very few, and therefore you can limit the overhead for Ceph or on the compute node. So you can, actually in Ceph, you can actually tell it, don't use more than X% of compute resource for Ceph, therefore guaranteeing that you have enough power for the or enough compute power for the rest of your compute environment. So in our case, we limited it to four OSDs, and we run the test to make sure that it can actually handle our virtual network function or whatever other workloads we put on these locations to make sure that we don't overwhelm the compute and therefore needing to add more compute devices to make up for the difference. Kiko?
Sure. So why is software-defined storage relevant? Like, why do we actually care about doing software-defined storage? In parts, it's because it allows you to do things like hyper-converge. If you had a storage array on the side and it wasn't software-defined, then there's no alternative. You can't take a storage array and run it inside a compute node. That's physically impossible, right? So software-defined allows you to run the software which does storage on the node itself. And it drives the same sort of operational qualities that you have with hyper-convergence in general, right? Reducing cost over traditional storage. You can get software-defined at a fraction of the cost of what the array would cost. You can scale storage with compute, so as you add more nodes, it's easy for you to understand, I can add an additional storage capacity with every node that I put in. And obviously, saving space and power. Looking at what is the big picture of this? So first, essentially, Ceph is sharing the local drives, which Nova is using for its own local storage. And it's very easy for you to cross that and separate it out. You get redundancy through replication, which means that even if you lose one of the individual nodes, you still have your data there. And it survives, for instance, taking a node offline to replace drives without rebalancing. You can use erasure coding to save on storage if you are doing a low latency, a workload which allows higher storage latency, like an object storage model. And just generally, you're reducing the requirement for specialized or more hardware to get to the same effort there. The last point I wanted to make is that hyperconvergence is interesting because if you look at the cloud, there is no special hotspot. If you put an array on one side and you put compute over here, the ports where the array is tied into will always be red hot because all the compute nodes have to go to that storage array. They have no other choice. As you hyperconverge, every node might even have local storage to itself. It may not even need to go over the network to fetch that one block that it was looking for because it has the block locally. But just generally, when you look at the switch, you'll see that utilization across the ports is much more even, much more uniform. So this, in a nutshell, is what hyperconverged and Ceph is around. As we said, and as Christian really introduced properly, this requires architectural thought and design, picking the right machines and ratios. If you'd love to know more about how to do it, please come and talk to us. We're experts. We've done it many, many times for hundreds of customers. We'd love to talk to you about how it's done. Thanks very much, Jacob and Christian.